All right, on this part, I just want to talk about some of the properties of definite integrals. These are in the book, mostly on page 379, but I want to go through them and kind of talk about why they make sense. Um, this first one says if you have a constant, if you're integrating a constant from a to b, then you just get c times b minus a. And that makes good sense because if you've got a constant function, let's say your function is going across here, and you're going from a to b, then the area underneath here, what you've got there is just a plain rectangle, and the width of the thing is b minus a, and the height is c. So that gives you the area right there. All right, this next one says if you have the integral of f of x plus g of x, then you can split that into the integral of f of x plus the integral of g of x. I'm not going to do a drawing for that one. This down here says if you have a constant multiplied by f of x, you can pull that constant out front and just do the integral of f of x. And here's sort of an example for that. Suppose you have a function. Let's say you had a function that looks like that. Well, if you multiplied this by 2, say that's f of x, there's some area underneath there. You know what, let's make it a constant function because that'll make it easier to see. So if this is f of x, we've got some area underneath here. If you then take 2 times f of x, well, that's just going to take this function and stretch it further up. And I think it's kind of obvious that the area of the green bit there is double the area of the black bit. And so that's, 2 being my c there. All right, this next one here, this says the integral from a to b is equal to the integral from a to c plus the integral from c to b. Now, just reading it off like that, it might not be that intuitive. But here's a picture that will make it make more sense. Here's my integral, or my function, and we're going from a to b. Let's say c is here in the middle. Well, we're looking at the area. This right here is that whole black area. Well, this is the area from a to c, and this is the area from c to b. So it's just saying that if you add up the area of one piece to the area of the other, you get the area of the whole thing. And on this one, notice I put c in between a and b, but this also works even if c is outside. So this works for any of them. And sort of the way to think of this is it's like they link up. You've got a to c, and then c to b. And if you put those together, it's kind of like these two sort of morph into one, and you wind up with a to b. All right, this next one, okay, this one there's a nice drawing for it. If your lower endpoint and your upper endpoint are the same, the answer is always going to be 0. And the reason for that is you've got some function over here. If you're just looking at just here, essentially what you're finding is the area of that line. And the area of a line, of course, is 0 because it doesn't have any width. So that's going to be 0. All right, this last one will make more sense after we talk about the fundamental theorem of calculus. But what this says is if you integrate f of x from a to b, if you swap a and b, it changes the sign there. And that'll make a lot of sense in another section or two. But for now, just take it on faith. Or take my word for it, I guess. Anyway, that ends this section.